Hi folks, and welcome back to this tutorial today where we're going to be looking at pixel and object extraction. Okay, so the first thing that I'm going to do is I'm going to open up my Anaconda prompt. I'm just going to navigate to where my code is. Bear with me 1 second. So this is where my directory is. So it's got all of my notebooks that have been kind of gathered together through this class. And what I'm going to do is I'm going to go Conda, activate SEER to actually activate our satellite image analysis virtual environment that we've got through Conda. Okay, and I'm going to open up Jupyter Notebook in this particular directory, and hopefully it's going to open up all of the different files that I've got saved here. And I'm going to go down into week 9, as that's where we are at the moment. I'm going to open up 9.01 Intro to Pixel Object Extraction. Okay, so just a little bit of kind of recap before we begin. Obviously, we've been covering a lot of ground within this class, and I just wanted to provide a brief overview of where we've come from and kind of where we're going. So at the very beginning, what we did was we went over an introduction to scientific computing in Anaconda. We looked at virtual environments, things like this, how you use Conda, the package manager as well. Then we looked at some introductory Python programming, so that was covering things like basic data structures all the way through to list of lists, okay, as that's where, that's how our image data is ultimately stored in NumPy arrays, okay, within that list of lists format. Then we looked at the different types of imagery sources that are available to us. We then covered a variety of scripts for actually downloading that imagery, okay, either via the Planet API or via Sentinel Hub. And then essentially we started to actually visualize this multi-band imagery that we could download. Then we covered how to actually clip that imagery that we downloaded for a particular area of interest, so we could just end up with a small area that we wanted to extract information from. And then today we're going to actually carry out that image pixel object extraction exercise. Okay, so we're going to be able to, in this case, actually extract the water from a river shape from an original image, and then later we can use that to do interesting things. Okay, so we can actually visualize that extracted data, so this is where we're going to go in the future. We can then look at how we actually carry out spatiotemporal analysis of these different kind of image sequences. I think that's the best way to put it. Okay, so we don't just get spatial information in terms of images, we also get time periods, and we can take that information, we can use that to create things like GIFs, for example. We can then look at how we actually use Git and GitHub to push our projects that we're going to produce, and then finally we're going to produce a coursework project in this class. Okay, so I think that that's given you a reasonably good introduction to intermediate to advanced satellite image processing. Okay, and actually I think the skills that you've got there are really exciting, because that is kind of state-of-the-art stuff. You know, being able to write script which does that download and processing of imaging. Okay, so what are we doing today? We're going to focus on this pixel and object extraction exercise, okay? So essentially we're going to focus on 3 learning outcomes. We're going to look at how we actually kind of visualize an image. I've given you a more basic example today that I'm going to cover. We're then going to look at how you kind of actually extract those pixels for different object types within an image. And then at the end, we're going to convert those pixels into shapes and extract them, okay? So we need to import a few packages for this particular example. Most of these we've covered all in previous classes. Okay, so we've covered Rasterio in detail. We've covered NumPy already many times. We've used GeoPandas to deal with shapes. And we've briefly touched on Matplotlib, but that's just the general plotting library, and that allows us to actually plot some of our either underlying data, or in this case, it can help us actually visualize the image that we're working with, okay? So, in this particular example today, we're going to be looking at an image of the Shenandoah River from the Shenandoah Valley, and you should be able to download that particular TIFF if you go to the satellite image analysis GitHub. So if you go to week 9, that image should just be there, Shenandoah Valley TIFF. You should just be able to download it So I can do that now just to show you that it's all working. Great. Let me just go through to QGIS. I can just drag and drop that in, and we can see that this is the image that we're going to be working with today, okay? So just to put that in some sort of context, here we have Washington, D.C. over here. And so we've got Maryland, Baltimore obviously is up here to the northeast, and then North Virginia here. And then as you drive out towards Front Royal, you end up going down the Shenandoah Valley, and here you've got quite a rural area, okay? So this is quite flat riverbed running through here, and then you've got some forest here, which runs up some steep-sided hill terrain, so it's quite rural relative to some of the other locations we've looked at. Okay, so that should give you some good context for that particular image. We can actually visualize it within our code, as you can see here, okay? So what I've done is, rather than looking at it just in the QGIS or any type of GIS software, we can actually just load it in as we've done here. So we're using that rasterio.open function again, and that basically produces a rasterio object, as we have here. We know that's a rasterio object because it basically tells us it's in read mode. We've got the they've got the data set associated with it. And then essentially what we can do is we can use this function rasterio.plot.show. And here what we're going to do is we're actually going to say that we want to read this rasterio object. You need to check the order of the underlying image colors. Okay, so we know that in multiband imagery we're going to have red, green, blue, infrared. It might not necessarily be that order. So for example, for a PlanetScope scene, the order is actually blue, green, red, infrared. So we're basically, to get it into RGB sequence, we need to go 3, 2, 1, okay? Referring to blue, green, red, and that should put it in the right order. So we have red first, then we have green, and then we have blue. Okay, so that's the first thing that we do, load that in, and then also we're doing this division here. Now I did pick up on why we do that division in previous classes. I just want to provide you with a bit more detail here, and that's because we're actually using matplotlib here, some of the functions from matplotlib, in order to plot these bands. And when you look at the actual underlying documentation from matplotlib, it says that your values have to be between 0 and 1. Okay, so they have to be float values between 0 and 1. Currently they are not. They're actually going to be integer values, I think, if you look at the underlying data here. So what we're doing is we're actually dividing them down so that they fall between 0 and 1. And when you've got that, you can nicely plot your imagery. If you fail to do that conversion, then basically every single value is going to be 1. And that means they're all going to end up being white for all of those colors that you have in your bands. Okay, remember the color circle that you might have learned at school. If you put together all of those different colors, you end up with white in theory. Okay, so if we divide here, then we have a nice differentiation between our color values, because they're all between 0 and 1, and that means that we're able to plot in geographic space this particular image that we've got here. Okay, so this is in universal transmercator projection, I think, so it should be, or something similar to that at least. So this is a projected coordinate reference system. Okay, we can move on. So that's an easy way to actually visualize your data in advance, and that kind of saves you from doing what we're going to do here, which is kind of separating out all those individual bands. Now it's nice to view it like we did in one kind of snapshot as before, but actually here what's kind of nice is then if you need to work with those individual bands, you can separate them out. Okay, so if we want to get red, green, blue, we're going to have to start with layer 3, layer 2, then layer 1, and then at the end here I've just put the near infrared band, which obviously is going to be the 4th band, and I've just separated it out. And remember before we said that our values are probably integers, and here's a good example of those integer values. Okay, so these are quite large. And that might cause a couple of problems along the way. So what we're actually doing as we load those in is we're actually also converting them into float values, okay? And that's going to help us later when we actually want to plot some of this data using different functions. Okay, so what do we do first? Well, the aim of this is that we want to actually extract as a polygon layer this underlying river area, okay? So there's the value that we have, the actual image, and we can see here that we have this river running through here. We want to extract that as an actual object. And before we do that, what we're going to do is we're going to create a new matrix, or you can call it a matrix, you can call it an array, so it's basically a list of lists, so it's the same dimensions as our underlying image. How do I know that? Well, you'll see here we're saying numpy.zeros, which is a function which just creates an array full of zeros. And then it takes the dimensions for that array, and actually if you look at what I'm giving it, which is the near-infrared.shape, whoops, it's going to give you the dimensions for our underlying image, okay? So we've got 2,281 pixels along the x-axis, and then we've got 1,359 pixels across the y-axis, okay? And once we've got those, whoops, once we've got those, we can have a look at our index. Okay, so we've got this index, which now is an array. It's a list of lists, and it's a similar shape to what we have for the other images. Okay. Okay, so what are we going to do next? Well, essentially, we're going to think a little bit about what we actually want to segment. Okay, so I've just provided you with a bit of an overview, kind of very basic introductory content from Planet University about what an image is. And the key point that I really want to emphasize here is that, you know, we have different wavelengths of light, essentially, we have different wavelengths within the electromagnetic spectrum, I should say, and when that actually hits an object, some of that is absorbed, some of it isn't, and that then affects basically the images that we take, depending on the wavelengths that are either absorbed or reflected, okay? So if you read through this, you can actually see a little bit of detail about that, okay? So it's talking about images containing a combination of bands. They each represent different wavelengths of light recorded by the sensor, and that could be an RGB plus near-infrared, okay? Obviously, we don't see the near-infrared layer, but it's extremely helpful here because some things absorb NIR, some things don't, okay? And you know, a little bit of an example here is that chlorophyll reflects a lot of the near-infrared light, which means it's useful for highlighting plants. Water absorbs a lot of the NIR light, so it's easy to distinguish green water from green plants. And actually, if you look in the link that I sent, they have this really nice example here where they basically show on the y-axis percent reflectance on a log scale, and then they show the wavelength on the x-axis. You've got the y-axis, the reflectance. You've got the wavelength on the x-axis, and then you've got different curves for different Earth features and their spectral signatures. Okay. So this is exciting. It shows that snow and ice has a high reflectance rate, which is understandable, and then you've got clouds a little bit lower, and then it starts to become a lot more nuanced by the time you get the different types of vegetation, different wetnesses of soil, basically, and then different types of water turbidity, okay, or clarity. Okay, so we can use this to our advantage, and today we're going to focus just on the water aspect, but you know, you could take any type of spectral signature and use this, this kind of information that we know about these signatures to extract certain layers from images, okay? So, we know that NIR is going to be absorbed by water, and that can be useful for what we're interested in here. So essentially what we're doing is we're re-specifying that water index so that it's, you know, a full array of zeros. The reason why I do this is so that if we play with this water index here, we're not trying to add values from one iteration on top of values that we create in the previous iteration. So essentially you want to be able to restart this fresh each time that you then try to kind of mask out certain pixels, okay. And essentially what we're doing is we're saying, okay, for the water index, allocate a value of 1 to any situation where the green metric, the green value of reflectance in that pixel is larger than the near-infrared pixel, okay. And what that means is that you end up getting 1s in those locations where the green is higher than the NIR, and that's most likely those locations where you've got water, okay, as you can see here. So we can run it based on that differentiation. We could even swap the direction of the signal, and we're probably going to end up with the opposite of that, so the antithesis. And essentially we end up with something that looks very similar, just in the opposite direction. So essentially here we've picked up all of the kind of plant material that's on land that most likely isn't water. But in this case, we're just going to focus on this first example here, where we try to actually get the river object, okay? So hopefully now we've managed to extract just those pixels that we think are water, essentially. And then what we're going to do is we're going to convert that just to make sure that everything within there is a float32 data type, which is necessary for them all to be in the same, all to be in the same data type. And then essentially what we can do is we can basically use this shapes function, which is part of this rasterio.features library here. And we can essentially take all of those, we can take that data that we have in our NumPy array, and essentially it will make shapes out of each one of these, okay? So we've got this generator object here. We know that's a generator object because it tells us. If we actually look at the length of that, so this is a list comprehension here, so we're able to break out that generator object into a list that contains all of those objects. We've got 63 objects within them. You can even look at what's in there if you're interested, okay? So these are basically GeoJSON data structures, and we have coordinates for those, in this case, polygons that we've identified. The issue, of course, here is that these are not in geographic coordinates, these are in raster coordinates, and therefore we're going to need to address that before we begin to extract our final data. Okay. So what we need to do is to just transfer those coordinates into geographic versions. So we have a function here. We know it's a function because it starts with DEF, so we're defining a custom function, and we're basically having only a single argument. That single argument is just a pair of coordinates, okay? And in this case, this is a function which we define, so it starts with def, we then have a colon, and I've even put a doc string in here just to help you understand what this function does, okay? So anything that you write in this doc string here, so these 3 sets of quotes followed by 3 sets of quotes, will essentially be a description of that function, and also if you were to generate your documentation from your code, then it would pull these doc strings through into your documentation that you might want to produce. So it takes that pair of raster coordinates, raster space coordinates, and basically we just use this rasterio function .xy, which just takes the raster coordinates here and then basically returns a pair of geographic coordinates. And we're essentially calling that this variable geographic underscore coordinates, and we're returning it, okay? So all this function is doing is something very simple. It's just converting from the raster coordinate space to the geographic space, and it's returning them in the same data structure. Okay, so this is the tricky bit now. You know, we've got shapes. we know we need to convert them into a different coordinate set. And we've got a function which allows us to convert those coordinates. And what we're doing is we're basically saying for a river shape in my shapes, so that's for a single GeoJSON within that my shapes list that we have, what we want to do is we want to get the coordinates first. So we're going to go into river shape, we're going to index into the coordinates part of the list. We're just going to get a list of all of those coordinates here. And then essentially we're going to actually transform them by using this function called a little list comprehension, and basically it transforms them into geographic coordinates, which then we're able to provide to this, this dictionary here. So this is a line string GeoJSON, and we're going to provide the coordinates to that line string GeoJSON and then append it to our output. Okay, so we're going to have a list of dictionaries, and those lists of dictionaries, the dictionaries themselves will be GeoJSON line strings, okay? So we're basically taking all of that information that we extracted, we're converting it into geographic coordinates, and then we're exporting them as we're preparing to export them as a set of GeoJSON objects, okay? GeoJSON data shapes. Now, next, what we can do, okay, is we can use this function from GeoPandas called GeoDataFrame, and rather than just specifying the GeoDataFrame, we can get it to take a list of dictionaries by using the from features function. So it's like if you have a list of GeoJSON objects, you can give it to the from features function, and essentially then you can export that to a file. Okay, so here what we do is we say geopandas.geodataframe.fromFeatures. We're going to give it the output, which is the list of dictionaries we just specified in this particular example here. We're going to specify the coordinate reference system, and actually I did just check when I put this into QGIS that it's EPSG 32617. Okay, and you usually have some information about this. So this is that UTM, Universal Transmercator projection, but it's for zone 17N, which you can probably see is kind of broadly the eastern coast of the United States and part of Canada down through Central America as well. Okay, so we can specify that at this point, because if you don't, then this GeoDataFrame that we're creating won't have a coordinate reference system. Okay, it doesn't know what that's going to be unless you specify it. So that's why I've specified it straight up here, and then we can even export that GeoDataFrame that we created using the to-file function that GeoPandas provides us with, and we can write that out, okay, as a dot shape, so an Esri shape file, and then we can basically do whatever we want to with that. So let's go and hunt down where that particular data is. So I need to go here, and I need to go to my satellite image folder. I need to go to notebooks and week 9, and when we get there, we should be able to load in this river shape that I've generated. Okay, so you can see the river shape just there. It needs some cleaning, which we'll get to in future classes, but essentially we've managed to extract that polygon of the river area all the way along this part of the river. Okay, great. So the exercise this week, and this basically is going to pivot into your assignment, is essentially to get the coordinates for Point State Park in Pittsburgh. So let's have a look at Point State Park. Great, so basically Point State Park is just here. And what I would recommend is that you just take a really, really small image shot, okay? So some of you I know have kind of blown out your free usage allowance from Planet, and I don't know how you managed to do that, but I suspect it's because you might have given a really large area of interest, okay? And that means that like every time you're downloading this giant image, and just remember that I'm not marking you, I'm not grading you on the size of your image. I'm grading you on whether you managed to complete the assignment or not. So the easiest way for you to complete the assignment is to use the smallest possible image, okay? Even if you used this image here, okay, so you just captured this part of the park, I'm perfectly happy with you using that, okay? So look, let's look specifically at what's in there. So you need to download a clear image for this area. You need to then clip that area to just this very small area that I'm referring to. Then use the code that I've put together here for you to actually extract the water features. And then preferably I'd like you to overlay the shapes that you generate on the original image and actually show me that you managed to extract this. You can even color them in, make it look like a pretty picture, for example, using a piece of GIS software. Critically review what you did in that process and then submit this work for the next assignment. Okay, and there should already be an assignment detailed within the GitHub here, so assignment 6 should all be written out. Okay, so you can follow up on that. That's due October 26th, and hopefully you're in fairly good shape for how you kind of put that together. Okay, so any questions, let me know. This is an exciting part of the course because you're really kind of pulling together all the things that we've learned over the last few weeks. And I think that, you know, if you can complete what I've set you here, then you're really going to be on your way for kind of delivering on the coursework project, which is really exciting because then you can use that as a future kind of job interview presentation or, you know, some sort of thing that you can talk about on your curriculum vitae, your resume, as something that you've accomplished. Okay, great. Well, don't hesitate to reach out to me if you've got any further questions, and thanks for tuning in today. Take care. Bye-bye.